Now look at it. Slowly we will take up a case. Let us first of all talk about this. Water is incompressible. Consider the case where there is a pipe with given area of cross section A and length L. Carrying water. When it is carrying water, say the water will be entering through this end and leaving through this end. Right. Everywhere, throughout the volume of the pipe, water will be there when it is carrying water. Think. You understand this? Water is there. It's full. Water is flowing. If I inject a colored particle, let us say it is this, into this water at one end. It will travel through the pipe. At t is equal to 0, if we inject this water particle and observe it in motion, depending upon the way in which water is moving, or laminar, turbulent, all those things, it will either follow a straight line path or curved path, a random path. Ultimately, you observe that at t is equal to t naught, it has come out of the pipe. Water is incompressible. This is the best example for us. What is the rate at which water is flowing through this particular pipe? The volume of water carried by this pipe per second is the rate. And that may be basically giving us the magnitude of the water current. Can somebody tell? What is the rate at which water is flowing through this pipe? Since water is incompressible, carefully see this. At t is equal to 0, when the particle enters this pipe, water was there in the pipe. In t is equal to t naught seconds, which is the time taken by this water particle to reach the other end of it, in t naught seconds, all the water that was present in the pipe at t is equal to 0 should have gone out through the other end. Correct? You agree this, no? incompressible. As this particle moves on, if it has moved to this position, this water is new. Whichever the volume that was there at this end would have gone out. When it is there at the center, half of the water to the left is actually new. Half of the water that was there at t is equal to 0 would have left the other end out and gone out. And now I think you understand that should have gone out through the other end, and so much of water only should have come into the pipe. Through the first end. So much of water should have entered the pipe. So much of new water, no? And so much would have crossed any cross section. You agree with this? If this pipe as such can contain 10 liters, would have gone out, 10 liters would have entered through this pipe, through this end, and 10 liters should have crossed this cross section, 10 liters should have crossed this cross section and gone to the other side. You agree with this? Please check it. 10 liters of new water has come, because of which through every cross section, 10 liters would have passed through to the right. So, the rate of flow of water is area of cross section A, volume, into L, capital L, into L by T0 seconds. In T0 seconds, through every cross section, the amount of the volume of water passed through it is the water present in the conductor, in the pipe. So many meter cubed per second, or if I have taken everything in centimeter, right? Centimeter cubed per second. With 1 by thousands of centimeter cubed per second is liters per second, correct? Because 1000 cc is 1 liter. I can talk about this. Like no meter cubed per second, centimeter cubed per second. Or so many liters per second, ultimately. Now, is it clear? Is it clear? Now, I created a potential difference. There is current flowing through a conductor. Important for us to understand again. Suppose I have a conductor for the sake of considering it, uniform cross section with cross sectional area A, length L. When the current is flowing through this conductor, suppose one specific electrons which is entering the conductor at T is equal to 0, charge is in motion. One specific electron which is entering the conductor at T is equal to 0 comes out of the conductor, the same electron. Let me put this electron E comes out at T is equal to T naught. If the number of electrons per unit volume of this conductor is N, this is the specific density of electrons per unit volume. Let us consider a case where one specific electron which is entering the conductor at T is equal to 0 through one end comes out of the other end at T is equal to T naught seconds. I'll say total number of electrons crossing any cross section of the conductor. You agree with this? In T naught seconds is what? All the electrons, because they are incompressible, that were present in the conductor while this electron is entering would have gone out through the other end. So many new electrons would have come in through the first end. So many electrons would have crossed each cross section in T naught seconds. What is that? En, number of electrons per unit volume into area of cross section into length. Where is the graph? This is the total number of electrons crossing any cross section in T naught seconds. Each electron carries E coulombs of charge, because of which total charge crossing any cross section of the conductor Q is equal to what? In T seconds. In T naught seconds is Q is equal to NaLE. NaL, number of electrons are there, each has the charge E. Now, the rate of flow of charge through any cross section of the conductor is equal to what? I, the current. NALE by T naught. In this, L by T naught is the distance traveled by the electron is L by T naught is what? Average drift velocity Vd, because of which the current I through the conductor is N A E Vd. Please check it. Area of cross section comes into picture. It's extremely important for us to know that this NAE, what is NAE for a conductor? Is the average amount of electron charge per unit length of the conductor. No, I'll tell you, if you have gone through this statement, derivation of the current through a MOSFET becomes quite simple. Without this, you should have seen textbooks in a complicated method deriving the expression for the current through a MOSFET from the source to the drain, of course. If you know this fact, if you know that the current is the product of average amount of charge per unit length of the conductor and the drift velocity with which it is moving, you can straight away get the current. Through the conductor I'm talking about. Average drift velocity it is. QL they call it. Is it clear? If we know, listen carefully, the number of electrons per unit volume of the conductor of cross section A and its velocity Vd, average drift velocity Vd, we can determine the current through that conductor as NAE Vd. Next topic